In this video, I will present our work, Fixed Parameter Tractable Submodular Maximization over Matroid. This is joint work with Shamisa Nematolaki, Arjun Baladu, and Jun Yao. I'm a postdoc at URIF. In this paper, we consider Matroid constraint submodular maximization. It's one of my favorite problems because it covers two of my favorite subjects, submodular function and Matroid. A set function is modular if it satisfies a diminishing return property. Basically, it says the marginal value of an element to a subset can only decrease if we add another element to that subset. For example, imagine you are having your lunch and you are eating a burger. Your friend brings you a drink. That drink makes your life much happier. But now imagine a different scenario where you are eating a burger and you already have a drink. Your friend brings you a second drink. That second drink does not make your life as happy as the first drink. And a Matroid is a set system that satisfies certain independence constraints. First, the empty set, and then for any set that is in the Matroid, any subset of that set should also be in the Matroid. And finally, it has to satisfy an augmenting property. Suppose we have two sets, x and y, they are in the Matroid, and y is slightly bigger, and then there must exist an element in y such that when we add that element to x, it results in a subset that is also in the Matroid. There's an important concept in the Matroid theory called the rank of the Matroid. In this talk, we denote the rank of the Matroid by R. It is simply the size of the largest set in the Matroid. A concrete example of Matroid is uniform Matroid, also known as cardinality constraint. An R-uniform Matroid simply consists of all subsets with size at most R, and the rank of this Matroid is obviously just R. In the problem of Matroid constraint submodular maximization, we are given a submodular function as a function oracle, which takes as input a subset and outputs the value of that subset, and a membership oracle for the Matroid, which takes as input a subset and tells whether that subset belongs to the Matroid. The goal is to find the subset in the Matroid that maximizes the function value. We denote the optimal subset by opt. This problem is NP-hard, so we need to resort to approximation algorithms. An alpha approximation algorithm always outputs a solution set such that its value is at least alpha times the optimal value. The landscape of this problem in polynomial time region is as follows. When the function is monotone, namely it's non-decreasing, then a 1-1/E approximation is achievable by a continuous greedy algorithm by Kalinescu et al. And a local search algorithm by Films and Ward. And this is the best we can hope for. Specifically, beating 1-1/E approximation would require n to the omega r queries to the function oracle. This is a classical result by Nemhauser and Wozi. For non-monotone functions, the picture is slightly unclear. The current best polynomial time algorithm is by Buchbinder and Feldman. It achieves a 0.401 approximation. For the lower bound, Kaharon and Vondrak first showed that beating 0.478 approximation requires 2 to the omega r queries to the function oracle. Recently, Qi showed that the same lower bound also holds for the cardinality constraint. In this work, instead of polynomial time algorithms, we consider fixed parameter tractable algorithms. For Matroid constraint submodular maximization, an algorithm is fixed parameter tractable if it runs in O(HR) times poly n time, where H can be any finite function and R is the Matroid rank. A concrete example would be, imagine you visit Paris and you take 100 photos. Among 100 photos, you want to select 9 photos to post on your social media. Even though 100 is a very large number, 9 is a very small number, so FPT algorithm would work very well for this application. FPT's modular maximization has been previously studied by Scrum and Rubinstein and myself in an earlier paper for the special case of cardinality constraint. The landscape for the cardinality constraint is similar to the Matroid constraint. When the function is monotone, we have 1-1/e approximation polynomial time algorithms, and beating 1-1/e would require n to the omega r queries to the function oracle. Notice that this lower bound implies even with FPT algorithm, we cannot do better than 1-1/e approximation. When the function is non-monotone besides the previously mentioned results, Rubinstein and myself designed a 0.539 approximation FPT algorithm for non-monotone submodular maximization with a cardinality constraint. The merit of this result is it shows that FPT algorithm can be substantially stronger than polynomial time algorithm. However, it also leaves the open question, what is the best possible approximation ratio achievable by FPT algorithm for non-monotone submodular maximization for the cardinality constraint and for the more general Matroid constraint. In this work, we close the remaining gap. Specifically, we design a near 1-1/e approximation FPT algorithm for Matroid constraint non-monotone submodular maximization. Our algorithm uses a runtime that has linear dependence on the total number of elements n and the exponential dependence on the Matroid rank r, and its memory usage is near linear in the Matroid rank r. We also design a near 1/2 approximation FPT random order semi-streaming algorithm, which I will elaborate on shortly. So now the new landscape becomes the following. For the polynomial time algorithms, it's still unclear what's the best possible approximation ratio we can get for non-monotone functions. For FPT algorithms, the approximation ratio of our algorithm for non-monotone functions matches the lower bound for monotone functions, and therefore shows that there is essentially no separation between monotone and non-monotone submodular maximization under the Matroid constraint in the FPT region. In the rest of the talk, I will first present our semi-streaming algorithm, and then I'll give you an overview of our near 1-1/e approximation FPT algorithm, which builds on our semi-streaming algorithm. Finally, I'll finish with some open questions. Let me start by introducing the random order streaming setting. In the random order streaming setting, elements arrive in a uniformly random order. A streaming algorithm maintains a small memory buffer, and if the memory buffer is near linear in the Matroid rank R, we will call such algorithm a semi-streaming algorithm. The algorithm is only allowed to query function oracle and membership oracle for subsets of elements stored in its memory. At the end of the stream, the algorithm has to output a solution set that belongs to the Matroid. Prior work by Feldman et al. Designed a near 1/2 approximation streaming algorithm with exponential memory. This algorithm works for more general adversarial order streaming setting and the Matroid intersection constraint. For semi-streaming algorithm, the current best approximation is 0.1922 approximation. This algorithm also works for the adversarial order streaming setting and it runs in polynomial time. Moreover, Shadravan designed a 0.432 approximation random order semi-streaming algorithm, and it runs in polynomial time. However, this algorithm only works for monotone submodular functions. For the lower bound, the previous work by Rubinstein and myself showed that any better than 1/2 approximation random order streaming algorithm requires n over r squared memory, even for the cardinality constraint, and therefore 1/2 approximation is indeed the best we can hope for this problem. Now let me present our near 1/2 approximation random order semi-streaming algorithm. It generalizes the streaming algorithm for cardinality constraint by Rubinstein and myself. It operates in two phases. The first phase is greedy selection, the second phase is a filtering phase. Let me unpack our algorithm. So we first divide the random string into two phases. The first phase is actually only epsilon fraction of the random string, and the second phase is the majority of the string. We further divide the first phase into R windows and greedily build a solution set SR from these R windows. Specifically, we build this solution set iteratively. In the ith window, given the set of elements that have already been selected in the first I-1 windows, we look at each element in the ith window that can be added to the solution set without violating the Matroid constraint, and we select the element that has the largest marginal contribution to the elements that have already been selected in the first I-1 windows. In the second phase, we use the solution set constructed in the first phase to filter the remaining elements, and we let H store the elements that pass the filter. Specifically for each element E arriving in the second phase, we add E to H if E is the better feasible choice than some element Si chosen in the first phase. Here, better means that E should have a strictly higher marginal contribution to the first I-1 element chosen in the first phase compared to element Si. And feasible means the union of the first I-1 elements chosen in the first phase and element E should still belong to the matroid. Notice that here when we do the comparison, we first round these marginal values to some discretization denoted by I. It turns out this rounding operator is crucial to achieve near linear memory. At the end of the second phase, the algorithm takes the union of the solution set SR constructed in the first phase and the set of elements H that pass the filter in the second phase and run an exhaustive search to find the best feasible subset of the union and return that as the final solution set. Now let me give you a proof sketch of the near one-half approximation. We first divide the optimal set into two subsets. We let OH denote the subset of optimal elements that are selected in the second filtering phase, and we let OL denote the subset of optimal elements that are not selected in the filtering phase. Then, by matrix-based exchange theory, we can partition the solution set SR constructed in the first phase into two subsets SL and SH, such that if we exchange SL with OL, or if we exchange SH with OH, the resulting set still belongs to the matroid. So now both SR and SL union OH are feasible solutions that are covered by the final exhaustive search. Specifically, SL is a subset of SR, OH is a subset of H, and therefore SL union OH is a subset of SR union H. And SR is obviously also a subset of that, so they are covered by the exhaustive search. We will prove that the value of SR plus the value of SL union OH is at least the value of opt union SR. This implies that one of the two solution sets must be a near one-half approximation. Specifically, this is because the value of opt union SR is at least 1 minus epsilon times the optimal value. This follows because SR is chosen from the first epsilon fraction of the random string, and therefore it cannot hurt the optimal solution much by submodularity. So it suffices to prove this inequality. To prove this inequality, we first decompose the right-hand side into three terms. On the rightmost, we have the value of SL union OH, and then we have the marginal value of SH on top of that. And then we have the marginal value of OL on top of the union. It's easy to verify the sum of these three terms are exactly the value of opt union SR. Similarly, we decompose the left-hand side into three terms. We keep the last term as is and decompose the value of SR into the value of SL and the marginal value of SH on top of SL. Now to prove the inequality, it suffices to show that for every column, the term on the top is upper bounded by the term at the bottom. For the last column, this is obvious, and for the second column, this follows from submodularity. The first column is a bit more complicated, but essentially this is due to the design of our filtering phase. Recall that OL are the optimal elements that are not selected in the filtering phase, and therefore we can show that its marginal contribution is actually worse than the value of SL. So that's the proof sketch. Please check out our paper if you are interested in further details. Now let me move on to the near 1 minus 1 over e approximation FPT algorithm, which builds on our streaming algorithm. The main subroutine of our near 1 minus 1 over e approximation FPT algorithm is a subroutine called continuous greedy filtering. It's a combination of our streaming algorithm and the fast continuous greedy algorithm by Bandanidi-Yulu and Vondrak. Just like our streaming algorithm, it operates in two phases. In the first phase, it uses a continuous greedy algorithm to construct a continuous solution, and in the second phase, it uses that continuous solution as a filter to filter the remaining elements in the string. So, as before, we still divide the string into two phases, where the first phase is epsilon fraction of the string. However, different from before, instead of dividing the first phase into R windows, we first divide it into 1 over epsilon epochs, and then we divide each epoch into R windows. So in each epoch, we will construct a solution set, and the continuous solution we construct in phase 1 is just the weighted average of the solution sets constructed in these epochs. Specifically, in the tth epoch, given the fractional solution built in the first t-1 epochs, we greedily build a solution set from R windows in the tth epoch, and we update the fractional solution by adding to it the epsilon fraction of the new solution set. So specifically, this solution set is built in the following way. In the ith window of tth epoch, we consider all the elements in the ith window that can be added to the current solution set without violating the Matroid constraint, and among them we pick the element that maximizes the marginal contribution to the current fractional solution, and this marginal contribution is measured by a continuous relaxation of submodular function called multilinear extension. In the second phase, we use the fractional solution constructed in the first phase to filter remaining elements. As before, we let H store the elements that pass the filter. Specifically, for each element E arriving in the second phase, we add the element E to H if element E is a better feasible choice than some element picked in some window of a certain epoch. Let me skip the details and describe what this subroutine actually achieves. We first partition the optimal solution set into two subsets, OH and OL as before. OH is a subset of optimal elements that are selected in the filtering phase, and OL is a subset of optimal elements that are not selected. The continuous greedy filtering subroutine guarantees that among all the solution sets we constructed in the first phase of the subroutine, there is a subset that is in the Matroid, and its value is at least 1 minus 1 over e times the value of OL. Our near 1 minus 1 over e approximation FPT algorithm applies this subroutine recursively as follows. If OL already accounts for 1 minus epsilon fraction of the optimal value, then by the above guarantee we know that S is already a near 1 minus 1 over e approximation, so we are done. If otherwise, we identify OH through exhaustive search and run the subroutine again on the refined instance given by the modular function f of x union OH and the Matroid contracted by OH. Then we repeat the above step for 1 over epsilon times. The point is that either the new OH also accounts for at least the epsilon fraction of the optimal value, which can only occur for 1 over epsilon times because there are only so much value from the opt, or we eventually reduce to the first case, in which case we know that the union of all the OH we contracted so far and the S in that particular iteration is a near 1 minus 1 over e approximation of the opt. That concludes the overview of our near 1 minus 1 over e approximation FPT algorithm. Now I want to finish by mentioning a few open questions. First, I want to mention that our near 1 minus 1 over e approximation FPT algorithm can be implemented as a constant path random order streaming algorithm, but this implementation will take exponential memory. So an open question is whether we can get the same approximation factor by a constant path random order semi-streaming algorithm. Moreover, our near 1/2 approximation semi-streaming algorithm relies on the random order. So an open question is whether we can get a near 1/2 approximation semi-streaming algorithm in the more general adversarial order model. This question is open even for monotone submodular functions. With that, I have finished my talk. Thank you for watching, and hopefully you'll remember submodular functions when someone offers you a drink.